In this video, let's learn about batch processing. We'll talk about the Hadoop ecosystem, about MapReduce, and Apache Spark. So batch processing is basically processing over batches or groups of data at a time. So you typically operate or process upon these batches on a fixed schedule, and you wait for these events to come in. You don't process them in real time. You wait for them to come in, group them, batch them, and then operate on them. So batch processing is widely used when you deal with big data, where the amount of data can't be stored on just one node, but you implement distributed storage to store these data across different nodes. And you schedule some interval to operate upon these batches of data. So you'll be using different frameworks to operate on them, the most popular one being Hadoop. So batch processing is collecting data over a period of time and then operating on it. The data is batched and only then operated upon. So the use case is for any big data use case, ML model training, daily sales reports, if you want to run analytics queries, etc. So when it comes to dealing with big data and operating on it, Hadoop has been the most popular open source framework for the longest time. So Hadoop is an open source software, a framework that consists of two major modules. One is a module that deals with actually storing data across the different nodes. So if you have your file system, and it's pretty big, you'll obviously chunk them and distribute them across your Hadoop cluster. So all that's managed by the HDFS module, the Hadoop Distributed File System. Your file system is distributed across the Hadoop nodes. The second major module is dealing with the actual computation or processing of this data that you have in your HDFS, and that's the MapReduce module. We'll talk about computation and MapReduce in depth once we understand HDFS and the overhead of the HDFS module. So Hadoop is a large modular framework composed of several smaller components that you can plug and play, but the two major components that are inbuilt in Hadoop is the HDFS and MapReduce. And a major use case of Hadoop is for big data storage and big data processing. So the core components is HDFS, which is the storage layer of Hadoop. It's designed to store large data sets across a cluster in a fault-tolerant, rack-aware manner. So fault-tolerant, let's say one of the nodes that contains a portion of your file fails, you should ensure that this node has replicas in place. So fault-tolerant. And what does rack-aware mean? We'll take a look at what rack-aware means in a short while, but just be familiar with this term. So over here is HDFS, and this is the architecture of HDFS. Let's say you have 4 nodes in your system and they all are configured with the Hadoop framework. So you designate 3 nodes to be the data nodes that actually store portions of your file system. And the master of them is going to be the name node. So the name node will contain all the metadata information. So if you tell Hadoop to store some particular file, which is terabytes long, the name node will take in that file and allocate respective data nodes to store in those blocks for the file. So data node 1 will store 100 blocks, the next data node will store the next 100 blocks, so on. So the name node will tell us the location of the blocks for the file. It'll tell us what data nodes they are in. The name node will also handle replication. The name node will tell data node 1 what all nodes it needs to replicate the incoming blocks to. So it tells us all the replicas, the files, the versions that they hold, and obviously the location of the replicas. So when the name node starts up, it asks each data node what files it contains, what versions of the files it contains, and let's say one particular node says it's holding a stale version, then the name node will ensure that it is replicated with the latest version from the primary data node containing that file. So when the name node starts up, it asks each data node what files it contains, versions of the files, and it stores all this in memory and it replicates files if necessary. So in Hadoop, you can configure the replication number. By default, it is 3, if I recall correctly. So in Hadoop, we expect a lot of reading compared to writing. So when you deal with batch processing, you already have these data events that come in, let's say from an IoT sensor. So you won't typically be overwriting the data in an IoT sensor. Whatever data is coming from the sensor, you're storing that and just reading on that and working on that. So in big data, we typically do a lot more reading compared to writing. So number one, if you want to read, the client will ask the name node for the file location. So let's say you will query with iotdata.txt to the name node. So your name node will know what all data nodes contain this file1.txt. So it knows that data node 1 will contain the first 100 blocks, data node 2 will contain the next 100 blocks, so on. Now let's say you have your data node 1 over here, which contains some blocks of your file that you want to read. And you'll obviously be having replicas of it as well. So let's call it 1 prime and 1 double prime. So when the client, when the external user queries the name node, this is the name node, asking for it the data node location that it can read from, the name node will try and assign a node which is in proximity to the client, so which is closest to the client. So it might assign 1 double prime to it. So we say the name node, the name node is rack aware. So what does that mean? So when picking replicas or assigning a data node to a client, it picks the most optimal location, hence the name node is rack aware. So what rack aware basically means is, let's say you have these data nodes with data in them. So rather than treating these individual data nodes as just a simple circle with some data in them, make use of the characteristics which are specific to each individual data node. So each data node will be having some specific storage. This might have bigger storage than this one. This might have a bigger CPU processing capability than this one. This one is in way more geographical regions with its replicas compared to this one. So the system does not treat each storage node as a homogeneous hardware agnostic entity, but rather one with some unique traits, making use or making knowledge of its capacity, its geography, its hardware characteristics in order to make decisions. So in your data center, you will have a lot of these racks, these metal trays. So what rack aware basically means is you have these different database nodes or data nodes storing some data in them. So rather than treating each data node as a simple circle with some data in them, make use of the inherent hardware and other characteristics which are specific to a particular data node. For example, this data node will have a bigger storage size compared to this one. This data node will have greater CPU computational abilities compared to the other two. Let's say this data node has better geographical replication compared to the other two. This is present in way more geographies. So any user can get direct low latency access to this one. So the system does not treat each storage node as a simple homogeneous hardware agnostic entity, but rather one with its own unique hardware traits, and it tries to make decisions based on that. So when a client tries to access some blocks for a particular file, the name node is going to be rack aware, and it makes decisions based on the individual hardware traits of the data node. So we'll assign one which is closest to the client. So where does the term rack come from? So you have the data center over here, and these data centers will have these metal stands, these racks, which will contain multiple of these computers. So one data center can have multiple racks, and you can have data center 2 with its own similar setup, so on and so forth. So typically, when you try to replicate, the name node will choose another computer in the same rack, because the amount of data that has to go from one node to the other node in the same rack, the data size is pretty big. You're dealing with big data, but the latency involved, the throughput involved because of the distance is pretty small. So the name node will always favor replication within the rack first. And if you recall, the default replication number in Hadoop is 3. So first you try to replicate within the rack. Second replication will be within the data center on a different rack. And the third replication could be a different data center, which is pretty close by to the first data center. So the probability of all three of these places where data is stored all going down simultaneously at the same time is negligible. So the name node is able to make all these replication decisions, assigning which nodes to read from or write from very effectively and very efficiently, because it is rack aware. It is aware of the hardware traits of each particular data node. So let's say you are the external user over here, and this is your Hadoop cluster. You have your different nodes running the Hadoop software, the Hadoop framework, and you want to read a file. So let's say this is the name node over here. These three are the data nodes, and you have one node that exposes the HDFS client-side API to read or write data. So the client will connect to the node to the HDFS API. So let's say the API endpoint is /read from HDFS. So the client will make use of this API that this particular node is serving and send in the file details that it wants to read from HDFS. This API will, under the hood, query the name node for the data node locations to read from. The name node is rack aware. It chooses the best data nodes to read from, considering the client location and the resources available, etc. And let's say it assigns this particular data node to read from. The API node will then read from it, read the data blocks from it, and serve that to the client. So the steps are as follows. The user queries the HDFS API, which under the hood will query the name node. The name node returns the locations of all the blocks or nodes containing the file, and the HDFS client API will use the block locations to connect to those data nodes. So our name node over here is a single point of failure. So if you want to have fault tolerance, you need to have replicas of the name node, and they should be in constant sync, and you want to strive for strong consistency as much as possible. So if you have watched the previous videos, you would have known that we typically employ Raft algorithm for consensus, and a popular Raft implementation when it comes to these configuration related data is Zookeeper. So you will use Zookeeper over here because you're dealing with configuration data. This is not application specific code. This is not business logic specific. This is config specific. So you achieve fault tolerance using Zookeeper. And if you recall, internally, Zookeeper is strongly consistent with the help of the ZAB, Zookeeper Atomic Broadcast Algorithm. So this is your Hadoop setup over here. You have a few data nodes down below, and you have a bunch of name nodes with its replicas. And let's say this NN over here is the primary name node for now. And this is the Zookeeper cluster with its own leader follower setup. Now, when NN over here tries to establish its leadership, it will create some location in the Zookeeper file system, let's say /leader, and insert its details. So all the other backup name nodes, when they subscribe to this same location, or when they try to create the same file directory, the same Z node, they'll see that someone has already created themselves. So they know that, okay, a leader is already chosen, and they'll just be in sync that, okay, NN is currently the primary name node. Again, this should all be obvious considering the previous video where we went in depth into how Zookeeper operates. So NN1 is the active primary name node. It'll try to initially create an ephemeral Z node, let's say in this particular location, /Hadoop HA my cluster active. Now NN2, the other standby backup nodes, will see or will query this particular location and see that, okay, someone has already been assigned the current active node, and they will be in sync that yes, NN is the current primary name node. Zookeeper will constantly send heartbeats to all the nodes that are connected to it, and will maintain and establish a TCP session. Now let's say NN1 were to crash. Zookeeper will wait for some session timeout, and then it'll delete the ephemeral Z node that NN1 created. Now all the other name nodes, the backup nodes that were subscribed to that Z node, will get a notification that, hey, the Z node has been deleted. The active node is no longer active, it's dead. So this will cause all the other backup nodes to trigger a new leader election process. So NN2, let's say, will try to create the same ephemeral Z node, and let's say it succeeds. If it succeeds, then all the other backup nodes will subscribe or will be in sync with NN2. But let's say it fails. It took some time for it to create this Z node, but in the meantime, some other node already created this particular Z node, and now it is the active node. Then NN2 will subscribe to that node. Now, mind you, Zookeeper cluster over here will only help in implementing fault tolerance for the Hadoop cluster. But you do have these different name nodes over here, NN1, NN2, NN3. You want them to be in perfect sync. You want them to have strong consistency. Zookeeper will not achieve this. Zookeeper does not help in achieving strong consistency for your Hadoop cluster. It'll only help determine who the current active node is. And if there is a failure in the active node, it helps trigger the next leader election phase. So it helps in achieving fault tolerance. So how are these nodes in perfect sync with each other? So one way to go about it is these nodes could implement Raft consensus among themselves. So let's say this one is the primary node and it gets some write. So it has to update or write some metadata. and this information needs to be in sync with all the other nodes. You need to have strong consistency. So you can do a quorum write over there, quorum write to all the other nodes. But this Raft consensus approach is not typically used because Raft was published in 2014 as an algorithm, but HDFS, Zookeeper as concepts, as implementations precede that. So the approach that HDFS implemented to achieve strong consistency among the name nodes was, let this be the primary name node and let these be some storage nodes, some temporary storage nodes. So any metadata write that it does, it writes to a quorum of them. And all these backup nodes will periodically poll from one of these storage nodes and they'll read from it. Now let's say the primary name node goes down. And let's say you have NN1 and NN2 as the backup nodes. And this is the journal nodes over here, the shared storage where you read metadata from and you write metadata to. Now let's say this is your Zookeeper cluster, and your Zookeeper cluster will notify all the backup nodes that NN is down. So this will trigger the next leader election process. Now that node, that backup node, who is able to create the ephemeral Z node, let's say on /leader, the ephemeral Z node first, that will be the new active node. So once NN2 is able to create this ephemeral Z node, it has acquired the lock on it. So Zookeeper will now not allow any other name node to create this Z node again, because you should have only one ephemeral Z node called /leader. So now NN2 is the leader, but NN2 could have read from some stale node. It could have some stale metadata information. So in order to be up to date, what it does is from the quorum nodes that are there, it'll do a quorum read. So it'll do a quorum read from the journal nodes and it'll update its state. So it's bound to have the latest and greatest state. So this is how you achieve strong consistency in Hadoop. It is with the help of this quorum journals. Your active name node will always write to a quorum of these shared storage nodes called the journal nodes. When the active node goes down, Zookeeper will trigger the new leader election process, and that backup node who is able to create the ephemeral Z node first will acquire the lock on it, and then it'll do a quorum read on these journal nodes to make its state up to date. Now, how is this different from Raft consensus? In Raft consensus, you don't have the concept of these shared storage nodes. Your primary node itself will do a quorum write to the other backup nodes directly. So number one, in Raft, you don't have to have this intermediate layer of shared storage. So this is an additional overhead. Number two, the leader election is indirectly triggered by Zookeeper in the HDFS process. But in Raft, the leader election process is wholly contained within the name nodes. So the name nodes themselves will understand that, okay, the active node is down. So it'll trigger a new leader election process among themselves, and that particular name node who has the latest and greatest state is bound to be the new leader. So the amount of overhead, the amount of data transferred over the network when compared to this quorum journal method employed in HDFS, where you have to talk to Zookeeper cluster, which is separate, some external entity, the amount of overhead in Raft is way lesser. But unfortunately, HDFS employs the quorum journal method. It does not employ a Raft. Zookeeper is ingrained with the HDFS module. So the current HDFS module is tightly coupled with Zookeeper, and ditching this to use a Raft between the nodes is not going to be an easy task. Let's end this section by talking about how huge writes are done in HDFS. So this should be pretty straightforward. Point one, the user will query the HDFS client API to write, let's say, 100 terabytes of a file. So the HDFS client will call the name node, and the name node is rack aware. So it knows how much storage is there in the data nodes, what resources are available, and will select a bunch of appropriate data nodes that you can write into. So the client API will provide this to the user, and then the HDFS client API will write each block directly. It will take in the input from the external user, and the HDFS client API will write each block directly to the primary data node, and it'll also specify to the primary data node what all replicas it should replicate to. Now, who provides this replica information will be the name node. So if we were to elaborate again, this is the API slash, let's say, write. The external user queries the API. The API under the hood will query the name node who is rack aware. And let's say the name node assigns this particular data node, let's call it DN1, to write data into. So the name node will specify that, hey, you should write to data node 1. In addition, the name node will also provide a bunch of replicas. So let's call it DN1 prime and DN1 double prime. So the name node will specify DN1 along with the replicas to the client API. The client API will take in the file content from the external user and will then send that information to DN1. So what does the primary data node have? The primary data node will obviously have the file content plus the bunch of replicas that it should replicate to. So who does the job of replication? It's going to be the primary data node. The primary data node will write content into itself and also make sure that it's replicated to the replicas that the name node has specified. Only once the entire pipeline is completed, the pipeline consists of adding content to DN1 plus content should also be stored and committed in the replicas. Only once all this is done, only then will DN1 send a commit success message to the client API. So the client will write each block directly to the primary data node, which pipelines it to the other nodes for replication. So let's say once you exhaust the storage limit for this particular data node, the name node will then give you an alternate data node, let's say DN2, to store the next 100 or so blocks. So in this way, you will be able to store in your terabytes, petabytes of data among your HDFS cluster. Now, HDFS is a distributed file system. It's a data store. It's not a database. What HDFS does is it stores these large files across multiple nodes. It provides fault tolerance through replication. It optimizes for reads of large files, and it's designed for write once and read multiple times. But it is not a database. It does not provide CRUD operations that you can do on individual records. You're dealing with unstructured files over here. You're not dealing with any structured data model over here. It does not support complex queries and joins efficiently. And so you can't call HDFS a database. It's a storage layer just to store files in a distributed fashion. So if you want to tinker with data, if you want to manipulate it, if you want to do CRUD operations, writes, updates, then you'll need to use a database that's built on top of HDFS. So you want to have a database that reads data from HDFS, maybe modifies it in place, and then flushes it back to HDFS. And that database, that abstraction layer, is called HBase. So HBase is a database that is built on top of HDFS. So HDFS is just a file storage layer. So if you want to update 5 bytes in some files, you want to perform a CRUD operation, you want to modify some data, it's very hard to do it efficiently with HDFS because you have to read that entire block from memory. And what is that block? That block is nothing but file. And if you want to update a specific region of that file, you'll have to overwrite the whole file. Modifying in place is not efficient. And then you have to write that same block back to disk. And again, this should also be replicated once you are done writing. So this is very time consuming, very inefficient because the data that you're operating on is unstructured. It's a file format. So doing write or modifying operations over here is not efficient. So in HDFS, there's no way to make an ad hoc edit for just one piece of data in a file. You're forced to retrieve the entire block, transport it across the network, work with that block, and again send that block back to be flushed to HDFS. So similarly, HDFS is terrible for cases where you just care about reading a few pieces of data. You want to retrieve just a few records. So HDFS is just a storage layer, stores the files, does not provide you with fine-grained tuning of what records you want or what records you want to update. So HDFS stores data as a simple file format. It is most ideal for batch operations where you care about mostly reads and not writes. So what do we care about targeted reads or targeted writes for real-time querying or analytics? So in that case, we'll have to use some database that's built on top of the HDFS storage layer, and that's the HBase. So HBase is a different plugin that you need to install separately and configure to run on top of HDFS. Throughout this session, I will be making constant references to HBase, and we'll compare it with Apache Parquet. Now, Parquet, we've seen in one of the previous videos on column-oriented storage. Parquet is not a database. Parquet is a file format like .txt, like .xl. So we'll compare and contrast when to use what. So a quick TLDR, for OLTP queries, we'll be using HBase. And for OLAP queries, we'll be making use of Parquet. So OLTP stands for online transaction processing, while OLAP stands for online analytics processing. So if you want to do analytics where you want to read large amounts of data, and the data that you're reading is just specific to one column, let's say you just want to find out the average of everyone's age, you just care about one column. So your data, your Parquet file will be arranged in that column oriented fashion. So if you care about doing a lot of analytics, you'll be making use of Apache Parquet. But if you care about OLTP transactions, normal CRUD operations, updates, deletes, overwrites, you'll be making use of HBase. We'll see why and how HBase is ideal for OLTP and why Parquet is suitable for OLAP in a short while. So let's compare and contrast HDFS with HBase. One is for a random access. From what we've seen, HDFS is not suitable for random access. With HDFS, if you want to read a specific record, you have to read the entire block, that large file, load it onto the disk, and then you can query your specific record. You have to parse linearly the entire file and then get your particular record. There's no efficient way to get to a specific record. But HBase is designed for random access. HBase provides you with a structured data model where your data is sorted on the basis of some row key, and then you can quickly do a binary search and retrieve it. We'll see more details in a bit. Structured data storage. So as mentioned, HBase organizes data in a structured format. It is in a column-oriented format, so it's NoSQL, while HDFS stores data as plain files that you provided. So what is the conclusion for plain HDFS? One is it's ideal for high throughput sequential reads or writes. It's not designed for random accesses. Number two, you'll use it if you process large data sets for machine learning activities, ETL pipelines, log analysis, etc., with minimal real-time querying or random access. This goes hand in hand with point one. Point three, HDFS excels for write once, read many workloads. You already have your data in place. You're not going to modify your data. You're just going to operate on it. You're just going to read from it. You're going to do batch processing on it. Data is ingested, stored, and it's going to be there. And then you process it in batches using frameworks like MapReduce or Spark. So example, if you have 10 million student records, you store this data in HDFS. You don't touch this. You don't tinker with it. You just read it, batch process it, and spit out the result. And you'll make use of some frameworks like MapReduce and Spark that will directly deal with this data that is stored in HDFS. We'll talk about both of them in the later sections of this video. But if you have a use case like social media analytics, where you provide a query like fetch user X's last 10 likes, then in this case, you're doing a random access, and it's better to use HBase. So it's fast lookup because data is structured on the basis of a row key. You can quickly locate to user X and get out whatever columns you need. So this seems very familiar with column-oriented storage. And as we've seen, column-oriented storage is excellent for analytical queries, and but HBase is mostly used for OLTP rather than OLAP, and we'll see why. So HBase is a column-oriented storage. When to use HBase and when to use Parquet. So let's see when to use HBase. HBase on HDFS provides a real-time random access. HBase is a column-oriented storage, NoSQL database that helps retrieve values quickly with the help of row keys. Efficient updates. You can update or delete rows in HBase very efficiently without having to rewrite the entire file. But this is not possible in Parquet. As we've seen in the previous videos, Parquet files once created are immutable. So if you want to update something in Parquet, you'll have to create another Parquet file, create the updates over there, and then perform compaction. And this has huge overheads. Updates in the case of HBase is very optimal. We'll see more details on reads, writes, the data model for HBase in a short while. So HBase, as mentioned earlier, is suitable for OLTP scenarios where data is constantly changing and we care about random read access. Let's talk about Parquet on HDFS. So Parquet, just think about OLAP, Big Data Analytics. It's very helpful for ETL pipelines. ETL stands for extract, transform, and load. So you have a repository of unstructured data. You will extract data from it, transform it into a structured format or for your use case, and then load it back. That's ETL. We'll talk about ETLs in depth in the last video. So Parquet is useful for OLAP, where you run analytics on big data, and Parquet files are immutable. So if you want to update specific rows, it requires rewriting the entire file. And coming to analytical queries, Parquet is good for analytical queries where you need batch access to a certain range. So in conclusion, you're going to use HBase when you need low latency random access, workload involves frequent updates, inserts or deletes, and you're serving real-time requirements. So you have a UI dashboard, and on this UI dashboard, you can put in any query that you want. You want to have details of a certain student, a certain user ID. You put in your query, and it's a random access that we need to implement. So that'll be done efficiently using HBase to serve real-time requirements. You're going to use Parquet when data is mostly write once and read multiple times for your computations. Data is mostly append only or batch ingested and rarely updated. And you need highly efficient analytics on certain columns, leveraging predicate pushdown. Predicate pushdown has been covered in the column-oriented storage video. It's basically a means to quickly sift through groups and quickly locate to the specific group that you're trying to read data from. So predicate pushdown helps you basically do binary search on groups of data at once. So back to HBase, uses the HDFS layer to actually store its structured data. So HDFS provides structured data through some data model, the column-oriented storage data model. We'll see details on that towards the end of the section. First, let's understand the architecture of HBase. So point number 2 for HBase is the most important point. It makes use of an in-memory LSM tree, and it is this fact that it uses an in-memory LSM tree that enables quick writes, quick key updates. So we've discussed about LSM trees and corresponding SS tables in the video on indexing. Do give that a watch. So I'm not going to go into the details of LSM tree, it has been covered, but a quick recap: you have this LSM tree, this tree structure that resides in memory. So any new update that you do, well, it's pretty easy. First of all, your structure is in memory, and updates, deletes will be done on the structure which is in memory. So it's pretty quick. Once the LSM tree hits a certain threshold size, it becomes too big, you will flush it onto the disk in the form of SS tables. So this tree will be broken down into different SS tables, and these SS tables are immutable. So that's exactly what HBase uses. HBase makes use of an in-memory LSM tree for quick writes or key updates, and then flushes these to the SS tables onto the HDFS storage. So you have your HBase. Once it creates those SS tables, it wants to flush it to disk. So it'll send those SS tables to HDFS. HDFS will accept these SS tables from the HBase layer and will push it onto the disk, and will also take care of replicating it to the other backup nodes as well. So HDFS will take in the SS tables. SS tables are flushed once the tree is filled. HDFS will take the SS tables from HBase. It will store it on its local disk, and it will also take care of replicating it to the other backup nodes. And of course, HDFS data nodes will also interact with the name nodes to say that, hey, I have these blocks for this particular file. So HDFS will take care of all that behind the scenes storage. So this is the HBase architecture. Let's have a quick look at the HBase architecture. So since HBase is built on top of HDFS, it more or less uses the same nodes. So in the case of HDFS, you have your data nodes over here. Similarly, you'll have your HBase data nodes, which are called the region nodes. So the region nodes are responsible for the LSM tree updates and creation of the SS tables and eventual flushing of the SSM tables back to the data nodes in the HDFS layer. So your region nodes are responsible for actually manipulating your data. And like in HDFS, you have a name node. Similarly, in HBase, you'll also have a master node over here. So why is this the case? So in HBase, we typically use it to implement partitioning. You partition data based on some ranges. So region node number 1 can contain data from users 1 to 100. Region node number 2 can contain data from users 101 to 200. And all this partition data, the metadata, is managed by the master node. And the master node can be frequently co-located as the same node as the name node in the HDFS layer. So on each of the bottom nodes, we have a region node. This is HBase specific, which is a separate process running on the same node as the HDFS data node. HBase uses range-based partitioning as its fundamental distribution strategy, and the partition metadata is managed by the master node, and the master node could be co-located as the same node as the HDFS name node. Every single region node is responsible for handling the LSM tree SS table flush to the corresponding data node in the HDFS layer. And it's responsible for handling the LSM tree SS table flush for its own assigned partition range. That is obvious. Let's now take a look at the HBase data model. It is a column-oriented NoSQL storage, though it differs in the structure as compared to the Parquet file format. So let's take a look at this SQL table over here, which is for user events. You have a bunch of user IDs with the timestamp. The event type that they do they click, do they purchase something, do they view something on a page, and what page they are interacting with, using what device and what browser. So the row key in this case can't just be the user ID, it'll be the user ID and the timestamp. So this should be the key. So this is the SQL structure. How will you represent the same thing, the same data in HBase? In HBase, what you do is you create groups of columns. It is, after all, a column-oriented storage. So you'll create a bunch of column families. Let's define two such column families. One of them is called the event family, which consists of the following column attributes: event type, which is over here, page, and timestamp. And let's say we create another column family, which is called the client family, which consists of the device and browser attributes. We then choose a row key, and the row key that is most appropriate is the user ID, timestamp in this case. Now let's see how it's stored on disk. So you'll have your row key over here, that's one row, and then all the column attributes that belong to the same event family will be clubbed together for this row key. So in this case, all the column values for the event family will be one after the other. This is for row key U001_1000. Once this is done, the next column family, all the column attributes belonging to the client column family, which is device and browser, will be clubbed immediately after. In practice, this is not actually used. What we actually do is the following. So let's say we have two column families, CF1 having column attributes A, B, and CF2 having column attributes C and D. So two column families, each with two column attributes belonging to it. And now let's say we have two row keys, R1, R2. These are two different records. What we typically do is on the SS table, this is the SS table which you eventually flush into. In the SS table, you typically devote one SS table, let's call it SS1, to one column family, CF1. Similarly, you'll devote another SS table, let's call it SS2, to the second column family, CF2. So how will you store the records? For R1, you will store CF1 with attribute A and whatever value it is, and CF1 with attribute B and whatever value that is. Same thing, R1, the remaining column attribute values will be stored in the next SS table corresponding to that column family. So you'll have R1 with CF2, the attribute is C and whatever value it has, R1 CF2 with column attribute D and whatever value it has. Once this is done, you will also have R2 data to be stored. So R2 can also be stored over here. R2's CF1 data can be stored. So R2, CF1's column attribute A value, R2's CF1 column attribute B value. Similarly, R2's CF2 column attribute D value and C value over here. So if a normal SQL table were to be stored like this, where row 0 will have all the column attribute names, let's say student ID, student age, etc. Row 1 will actually have the corresponding values for those column attributes. How will HBase store it? HBase will store it in this fashion, where you'll have row 1, R1, the key with the column family and the column attribute and corresponding value. Row 1, same column family, but a different column attribute with its value, corresponding value, so on and so forth. Now, this example we've already seen. Let's assume we have two row keys R1, R2 with two column families CF1, CF2, each having two column attributes corresponding to it, C1, C2, C3, C4. So the physical representation will be on SS table 1, you'll have R1 with CF1, R2 with CF1, and SS table 2, R1 with CF2, R1, R2 with CF2. So depending on the number of column families, we can have the same amount of LSM trees. So mind you, an SS table will correspond to one column family, and SS tables are flushed from LSM tree. So you'll need to have one LSM tree for one column family and the other LSM tree for the other column family. So let's say worst case, you're updating all the attributes of a particular user, then in that case, you'll have to touch upon all these different LSM trees, but no worries because these LSM trees reside in memory. So dealing with them is not that inefficient. So depending on the number of column families, you have the same amount of LSM trees, and on flushing, each SS table will then pertain to just one column family. This becomes very efficient when you don't have to deal with multiple attributes at the same time. And most real life cases, you're not updating all column values at the same time. You're just updating one or very few columns. For instance, update the last login time of a user. You're not updating all the column values for that particular user, just one attribute, one column family. So in that case, the amount of data that you have to touch is very minimal. You're just dealing with very specific amount of data that you actually are going to modify on a frequent basis. So from an HBase point of view, LSM tree is called memstore, memory store, and the SS table is called the H file. This is from an HBase context. SS table and LSM trees, these are indexing techniques and they are general data structures, but the HBase specific implementation of LSM trees and SS tables are called memstore and H file respectively. H file, in addition to being an SS table for all intents and purposes, will also have awareness about the column families. So SS tables, when you flush content from LSM trees to SS tables, they store data in a structured format, but H files are more column family oriented. So H files store data in a very specific fashion. Like in this case, they group records belonging to the same column family together. And this makes retrieval access very efficient on the basis of row key. But for all other intents and purposes, SS tables equals H files, LSM trees equals in-memory store. Now, what is the benefit of the column family separation? I hope this should be obvious by now. We can grab and operate upon only those column families, those columns that we care about. So updates will be very efficient because you just have to tinker with that particular LSM tree that deals with that column family. Similarly, if you want to read certain columns, you just have to access that SS table, which caters to your column family, your column attributes that you want to read. So the amount of data that you have to deal with is very minimal. Number two, why does HBase excel at OLTP compared to Parquet? And the reasoning for this is exactly the same. HBase is optimized for selective access. So in the SS table, in the H file, you are storing data on the basis of your column families, and you're also sorting it. The data is sorted on the basis of the row key. You have R1 here, R2 here, R3 here. All you got to do is a simple binary search. So a random access is very efficient. And this is especially true when you don't have to read all the values. You just want to query what the last login time for a user is. So that could be belonging to column family 1. So let's say you have hundreds of column attributes. You just care about one or two column attributes periodically for periodic access. So the amount of data that you have to deal with is very minimal. So HBase is optimized for sparse selective access, only few columns for a certain row key at a time. Each file is already sorted by the row key and grouped by column family. So accessing is very trivial as the amount of rows read to narrow down the record is minimal. All you have to do is a simple binary search. What about Parquet? What if you want to access a random row from Parquet, a random record from Parquet? If you recall, Parquet is stored in this fashion. So let's say you have two attributes. One is the student age and the other one is the student marks. So all the values for age will be stored one after the other. And only after you're done storing all the values for age, you'll store all the values for marks, one after the other. But what if you have a million students? You won't be storing million student ages here and after that a million student marks here. What you typically do is you will divide them into row groups. So in one Parquet file, you will store just 100 student records. So this will be age for students whose roll numbers are from 1 to 100. Same thing over here, 1 to 100. And on a different Parquet file, you'll store the row group will be for students from 101 to 200. So if you want to pick out a certain student, you'll have to locate that particular row group, go to that Parquet file. Once you're at that Parquet file, let's say you want to read all the column values for that particular student. You want to do a normal OLTP transaction. So you'll have to go to C1 in this case, do a binary search and then get that particular student record, skip all the remaining values and then go to C2, grab that particular record over here, do binary search, you're doing predicate push down, and so on and so forth for all the hundreds of attributes you have. So for OLTP queries, this is not an efficient process. The amount of data that you have to deal with, because of the way data is structured in this case, is suboptimal. Compare it with how you're storing data in the case of HBase in H files. In H files, you're grouping it on the basis of column families, but the way we are storing it is all the data for R1 and only then all the data for R2. So yes, in the worst case, let's say we do have a few H files. So this has CF1, this has CF2, and I want to query all the columns, the entire record for R1. Yeah, in the worst case, I do have to touch CF1, I do have to touch CF2, I do have to touch the other third H file as well. But the amount of data I have to deal with is very less because all the data for R1 is already grouped together. All the data for R1 is already grouped together as compared to Parquet's structure, where R1 is over here, then I have to skip some data and go to C2 and read R1's second column value over here, so on and so forth. So Parquet is clearly better for OLAP. In the case of OLAP, I just want to find out the student averages from roll numbers 1 to 100. Simple, just go to this row group, go to the column, and you already have all the records, the age records clubbed right next to each other. So you can do a simple aggregate function over that. But that becomes a little tedious when you talk about the H file structure. So that is point number 1 of why HBase excels at OLTP and why Parquet excels at OLAP, because of the way their data model is, the way that we are actually storing data on the disk. So HBase is optimized for selective random access, while Parquet is optimized or designed for true column oriented storage. Number 2 is write performance. Parquet files, as mentioned, are immutable. So if you want to update something, you have to rewrite the entire Parquet file and then perform compaction. This is very costly. And Parquet is designed for batch ETL processes where you're writing stuff onto the disk once and then you're reading from it multiple times later. It's not meant for real-time querying. And there's no such restriction in HBase. If you want to do an update, it's pretty easy. The LS entry is residing in memory. Just update the node, create a new node, and then eventually flush it to the SS table and perform compaction. The final question that we need to ask is, why does HBase have the grouping on the basis of column families? Why do we have these different SS tables, these different H files that are distinct from each other on the basis of the column families? Why not just use SQL if you care that much about OLTP? And there are 2 reasons. The first one is schema flexibility. If you were to use traditional SQL and we had 10 columns today, but what if we need to have a facility to add an 11th column tomorrow? In that case, that'll be pretty expensive to accommodate. So in SQL, if you want to add a new column, it is a very expensive operation that involves possibly a rewriting of the entire file. And this is obviously not preferred. What about HBase? How do you accommodate new columns or new schemas? It's very easy. All you got to do is just assign the column to some column family. And for subsequent inserts, push that into the respective H file. All you have to do is update the LS entry, which is in memory. So let's say this is your existing H file for CF1. You have R1, CF1 with 2 column attributes, and you want to add a third column attribute C3 to C F1 to column family 1. So when you add C3, all you got to do is update the LSM tree. So you have your LSM tree over here in memory. Just update the LSM tree to support this new C3, and that is pretty easy. It's a small data structure in memory. So your LSM tree will take in data belonging to C1, C2, C3, and when it comes time to flush, it will flush it onto a new H file. That's how flushing works. So it'll create a new H file, and this new H file will contain C1, C2, C3. But you also have your existing H file that does not have C3, just has C1 and C2. And your new H file has C1, C2, C3. No big deal. Periodically, what is done is you perform compaction. You'll perform a merge. So the final H file will have C1, C2, and C3. So when you add C3, the new data goes to your updated LSM tree, which is in memory, and is eventually flushed to a new H file over here, R1, CF1, C3. You'll do periodic compaction, and then you'll have this. So this is your new H file. And that's how easy it is to accommodate new schema changes. Point number 2 is sparse data problem. SQL, every row must have space for all possible columns. This becomes a big deal when columns can be nullable. So take this case of two users. User 1 is homeless. User 2 is pretty rich, has many properties. So user 1's address 1 is null, address 2 is null. User 2 will have some addresses. Now, when you scale this to millions of records, you'll have a lot of wasted space because of this rigid schema. In the case of HBase, you don't need to have all the column values, all the column attributes for all the row keys. So if you have row key R1, you'll have CF1, let's say C1 with some value. It'll have CF1 with, let's say, C2 and some value. It'll have CF1 with, let's say, C3 and some value. But let's say C2 and C3 can be nullable. They're not needed. Then in that case, row 2 CF1 is needed. It's a mandatory attribute. Let row 2 skip on C2, let it skip on C3. You don't need to add it. So this will be the H file structure where C2 and C3 are nullable. So in HBase, you can have variable number of columns for a certain row key. This is incredibly powerful. So user 1 profile name John, user 2 profile name will be Jane, and profile theme is dark. So you have two columns, obviously belonging to the same column family, but for the other row key, you just have one column that you actually care about. So in HBase, each row key can have variable columns. You're not confined to a rigid schema. So it's also called a wide column store because you can have multiple columns, variable amount of columns for a certain user, for a certain row key. Even Cassandra has this functionality of variable column attributes per row key. So all these space optimizations, they do add up when you talk about data and scale. And space is often directly tied to computation performance. The amount of data that you have to sift through, all this adds up. It eats up from CPU time. So lesser the amount of space that you consume, the better. And HBase excels at that for OLTP queries. I think these two questions that we covered for HBase are extremely important. Let's have a quick recap of these two questions and the points that we covered under them before we move to MapReduce. Number 1, why does HBase excel at OLTP compared to Parquet? It all has to do with the LSM tree SS table structure. HBase is optimized for selective access because your H file is already sorted on the basis of row key and you're already grouping it by column family. So if you care about just a few columns, you direct your query to that particular column file. It already has lower amount of data. So the amount of data you're dealing with is pretty low. And you can just do a binary search over here. Whereas in the case of Parquet, your data is not clubbed together for a certain row key. You have to access a specific column value over here, then skip past a lot of data and go to the next column value, so on and so forth. So Parquet is better for OLAP cases. Number 2 is write performance. Parquet files are immutable, but HBase supports mutating your data objects through the LSM tree in-memory structure. Question 2, why does HBase have group by column families? Why not just use SQL if you care about OLTP? One is because of schema flexibility. SQL is very rigid in terms of its schema. And number 2 is sparse data problem. Again, SQL is very rigid in its schema. Even though fields can be nullable, you still have to make space for them. This is not the case in HBase. Let's now talk about MapReduce. Before that, a quick spoiler. MapReduce is outdated. For all intents and purposes, we use Spark in modern day distributed systems with big data. We'll see why towards the end. So MapReduce is basically a programming model or a programming approach to dealing with computations of big data distributed across your nodes. So it consists of a map phase, a shuffle phase, and a reduce phase. So MapReduce is a concept, an approach, and the Hadoop specific implementation for MapReduce that reads data from HDFS, does the map shuffle reduce cycle, and then flushes it back to HDFS. That is called Hadoop MapReduce. And this is the second core component of Hadoop other than HDFS. It's the ingrained Hadoop MapReduce implementation. So what is a map phase? Map phase consists of converting your unstructured input data to a standard structured key value pair. So you have your input object and you're converting it to a structured key value pair format. So one example could be a word count in a large document collection. So let's say this is your input data. You have these different files, and file 1 has hello world hello, file 2 has world of data, file 3 has hello data mining. So all this data is distributed across nodes, and the end outcome is you want to know what are the word counts. So hello is appearing 1, 2, 3 times across the different nodes. So how do you put forth this list? How do you do the computation over this big data? So let's start with the map phase. In the map phase, you will take in your input object and convert it to structured key value pairs. So you'll have mapper 1, which operates over node 1's data, hello world hello, and the output will be hello 1, world 1, hello 1. Similarly, for file 3, which has hello data mining, you'll have the final output being hello 1, data 1, and mining 1. So the word in this case is the key, and the value is the occurrence in that local node. What about the shuffle phase? In the shuffle phase, you'll group all values on the basis of the key, take the hash, and submit it to the reducer node. So you have your individual nodes over here. You did the map phase is done. Then on the basis of the hash of the key, on the basis of hash of hello, or on the basis of hash of world, you will distribute that data across different nodes. So what does this achieve? So let's say hash of hello goes here, hash of world goes here. The hash of hello for this one will go on the same node as this. So what the shuffle phase does is all the words, or basically all the keys, the same keys will be located on the same partition, right? So what this does is groups all objects having the same key in one partition. So if this is your node 1, this is your node 2, all the key value pairs having the key hello will be over here. All the key value pairs having the key as world will be over here. All the key value terms having the term data, the key as data, will be over here. So in the shuffle phase, you'll group all your values on the basis of the key, take the hash, and submit it to the reducer node. So the reducer node is the last and final phase of a MapReduce job. So the reducer node will, let's say reducer A has all your key value objects where the key is hello. So it will simply group it and spit out what the final object is. So it knows that it has 3 key value terms where the key is hello, and it will generate the output. Hello corresponds to 3 terms. Same thing for reducer node B. It has all the key value objects where the key is world, and it'll spit out what the aggregate is, which is 2. It can do this easily because all the keys are already aggregated and located on the same node. So the reducer phase will operate upon the key value lists if it received, perform some aggregate function on it, and flush it to HDFS. So the output of the reduce phase is pushed into HDFS, and HDFS will take care of the background tasks like replicating it and interacting with the name node to specify what data blocks it holds, so on and so forth. So in general, the same nodes that were part of the map phase can also function as reducers. So it depends on the amount of load they have. So let's say these were the initial nodes and you did the map process. Now comes the shuffle process. It doesn't necessarily mean that when you shuffle them, you'll shuffle them to brand new nodes. That doesn't necessarily have to be the case. If these nodes themselves have enough resources, have enough computation, have enough storage, the hash output can be nodes among themselves itself. Same thing with the reduce phase. So you have these 3 different phases. might look like, from a logical view, it might look like these 9 nodes are 9 distinct nodes, but that need not necessarily always be the case. These can be the same nodes. This can be node 1, and maybe node 2 for this case, so on and so forth. So who decides where to place the tasks? So you submit your MapReduce job. You want to operate, let's say, the word count over this big data. Who assigns the nodes which will run the map job? Who assigns the nodes which will run the reduce job? So that will be the job of the YARN scheduler. YARN stands for yet another resource negotiator. It is a resource coordinator basically. So it keeps track of the available resources across your Hadoop cluster. It keeps track of data locality. So ideally, if the data that you want to operate on is, let's say, ABC, so YARN will try to schedule that task on this node itself that already has the data that you want to operate on, ABC, rather than moving ABC to some other node and operating on that. So YARN prefers data locality. If you already have the data on the node, let's try to perform computation on that same node. This is obviously possible only if the node in question has enough compute resources. If that's not the case, well, you can't, data locality won't help in this case. You're forced to move data across the network to a better node. And yes, YARN scheduler will also help in load balancing. This goes hand in hand with point 1, available resources. So it constantly keeps track of what nodes have what resources available at present, and based on that will distribute tasks accordingly. We'll talk a little bit more about accepting MapReduce jobs, about task distribution, about YARN, and the MapReduce architecture in a bit more detail towards the end of this section. So we can also chain MapReduce jobs to implement complex functionality. So let's say after the final output of the MapReduce job 1 is the word count. So hello 3, and let's say world is 3 and hi is 1. Let's say now you want to also find out all the words or the number of words where the count is more than 5. So that needs to be another MapReduce job that you can trigger. So the flow is as such. You have your initial nodes over here. These nodes will read the data from HDFS. They'll do the map, they'll do the shuffle, they'll do the reduce tasks, and then the final output will be stored back onto HDFS. When you trigger MapReduce job 2, you'll read back that data from HDFS. Those data could be anywhere. They could be scattered across the Hadoop cluster. You'll again do a map, reduce, shuffle cycle, and you'll spit that back onto HDFS. So this is the cycle. So using MapReduce, you can implement any complex functionality, but this often involves chaining multiple MapReduce jobs, and that is a major detriment. We'll see why when we talk about Spark. So the eventual output is then replicated to the corresponding replicas of the HDFS node. So what are the major benefits of MapReduce? If a computation step fails in some node, you don't need to redo the entire MapReduce job. You just need to restart the node or assign one of its replicas to do it instead. So what does this mean? So let's say your MapReduce job has 3 parallel pipelines. So this is the map phase, this is the shuffle phase, this is the reduce phase. So you have node 1, you have node 2, node 3 operating upon portions of your data that you want to perform some computation on. So node 2 is going fine, node 3 is going fine. Node 1, let's say node 1 fails, the node shuts down. So the advantage of MapReduce is you don't have to re-trigger your entire MapReduce job, and you don't need to have node 2 and node 3 starting from scratch. Their pipeline is mostly independent. So all you got to do is find the replica for node 1, let's say it's 1 prime, and just re-trigger the process over there. So you're not starting the entire MapReduce job from scratch. You're just restarting it on one specific pipeline, and the overhead is comparatively minimal. So failed mappers or failed reducers are restarted independently without affecting any other node. So let's talk a little bit about YARN, which is a resource coordinator, a resource negotiator. It's called yet another resource negotiator. So there are 2 major components to YARN. One is the RM, the second is the NM, the resource manager and the node manager. In addition, there is a third term called AM, which is application master. We'll take a look at all 3. now. So RM stands for Resource Manager. It is the main master thread. You'll have only one per Hadoop cluster, one per MapReduce cluster. And the workers of the resource manager, they are called the node managers. They're the worker threads, and you'll have one per node. So what is the responsibility of the RM? RM will know what resources each node will have, what is the computational abilities of each node, how much load they currently have. So it knows the available CPU memory across a cluster. So the RM will do the global resource scheduling. It does application level management. It accepts job submissions. If you have a MapReduce job to submit, you will submit it to the resource manager, to the RM. And the RM prioritizes the same node compared to same rack and then compared to same data center. So what does this mean? Let's say you have your rack over here and your rack will have different nodes. And let's say you want to operate on data XYZ. So XYZ is on this node. So the resource manager will try to prioritize this node itself to do the computation for the MapReduce job. If that is not possible, if its CPU is pretty terrible, it will allow it to migrate the data from this node to the other node, which is on the same rack. So it tries to pick out something which has better computation, better storage on the same rack. If even that is not feasible, then it'll move to another rack or maybe another data center. So that was the RM. So the RM is the main resource manager. It knows, it is rack aware, obviously, and it will know the hardware utilities, the hardware constraints of each of the data nodes, and it'll accept the MapReduce tasks. The client of RM is called the NM, the node manager. So assuming this to be your data node, you will have your node manager as a separate process that resides on this data node. And when the resource manager commands the NM to perform the MapReduce job, some map phase or shuffle phase, the NM will create a thread, and in this thread, you'll have your MapReduce task running. So the NM responsibilities are to actually execute your MapReduce job. The RM is to take care of the bigger overhead of assigning which node to run on, of assigning what tasks will be run by which data nodes, so on and so forth. So the NM responsibilities is to spawn a container, spawn a thread to run the assigned task, and it will constantly report the node status to the RM. Because of this constant reporting from the NM to the RM knows about the local health, about the local resource utilities, resource capabilities of the current data node. So what happens during task submission? The client will contact the RM. The RM will spawn an AM. So this is the third and final term for MapReduce. So when I earlier mentioned that the RM, the resource manager, will command the NM, the node manager, to run the MapReduce task, that was a gross oversimplification. This does not happen. What actually happens is the AM actually tells the NM to run the MapReduce job. So you have your RM over here, your resource manager. Down below is the data, the name node over here, NM. And in the middle, you have your AM. Your client will submit some MapReduce task to the RM, and the RM will pick some free node which has compute available to spawn the AM process, the application master process. So when the RM gets the MapReduce job, it will find some suitable node which is available, which is free, and it will trigger, or it will create the application master process. This application master process is specific to a certain MapReduce task. So if the RM gets another MapReduce task, it'll find another node, and it'll spawn another AM specific to that MapReduce task. Now, what does the AM do? The application master will analyze the MapReduce task that it received from the RM, and it'll see that, okay, it needs X mappers, it needs Y reducer nodes, and it'll send all this low-level detail information to RM. So it basically requests for resources, requests for nodes, requests for compute or storage from the RM. Now the RM is rack aware because it receives constant inputs from the node managers. So it knows what nodes currently have resources available. So the RM will then tell the AM that choose data node 1, choose data node 5, choose data node 6 for whatever tasks you've been assigned. The application master then directs the node manager of data node 1, of data node 5, and of data node 6 to spawn a process and run the MapReduce task for it. So the node manager will then spawn a thread and run the MapReduce task. So your MapReduce task goes to RM. RM will spawn an AM specific to that task. AM will analyze the MapReduce task and request for resources from the RM. RM will submit a list of resources, a list of data nodes that are suitable for that particular MapReduce task. The AM takes that information and orders the NM to perform those MapReduce tasks, those specific map, shuffle, reduce phases. The NM, in order to implement them, will spawn a thread, and in that thread, you'll be running that code. So one client contacts the RM. The RM spawns an AM, which is a special container to manage a specific job. The AM requests the RM for resources. RM allocates containers on various node managers. AM tells the node managers to spawn containers and assigns them tasks. So if the map or the reduce task fails, who is responsible for finding out the replica and retrying that task? So it will be the AM. The AM will constantly be querying the status of the MapReduce task. So it retries on other nodes. And lastly, the application master is responsible for coordinating the shuffle phases and ensuring that data is correctly distributed across the nodes when it comes time to shuffle them. By the way, what does a client who wants to submit a MapReduce job to the resource manager send? So in code that you submit to the resource manager, you will mention the file name from where to read the data. You will define your mapper code, your mapper function. You'll define your reducer function. You can do that in Java. And the application master will take care of the rest. So what is the conclusion? MapReduce is a very useful programming model and the Hadoop specific implementation, which is the Hadoop MapReduce framework, for performing big data batch processing on a schedule. However, MapReduce has some major performance flaws, and in practice, in today's scenario, it's not used widely. We prefer to use Spark. Before we see why Spark is better, let's first take a look at how we do batch data joins. So often during these batch computations, you'll have to join data from that is present across different nodes. You want to join multiple data sets together, sort of like a SQL join. So how do you do this efficiently for big data that is distributed across nodes? So we'll see three different approaches. The first approach is sort, merge, join. This one will always work. It's a general approach. So let's say you have your two data sets and you want to perform a join on them. So dataset 1 is distributed across node 1 and node 2. Let's say you have some key A and the value is 5, and dataset 2 is also distributed across nodes 3 and 4, and you want to join them on the basis of the key, the join key. So what the sort, merge, join says is, well, first sort the data which is present in your local node. So node 1, sort the data which is local to you, same for all the other nodes. Then you'll perform a merge join. So you'll do the hash to make sure that all the objects having the same key are relocated to just one single partition. So in this case, all the objects having the key A are located on one partition. Same thing with B, C, and D. So you've sorted it and you've done a merge join. And over here, your reducer can simply operate on that. So you've effectively done a batch join over here. So this is a general approach, and we assume that there's two data sets with two partitions each, and for every single partition, we sort data which is local to it, and then on the basis of the hash key, we repartition the data. Now this is important because the data is sorted in the repartition or merge phase. We are just merging two sorted lists. What does this mean? So you have your nodes over here. Let's say it has B and A. So this is dataset 1, this is dataset 2, which also has B and A. And let's say, and you perform local sorting. So this will be converted to AB, same thing with this AB. And let's say both AB will be hashed and they'll be sent to partition P1. Now when partition P1 receives data from A, it'll receive it in a sorted order. So partition A receives AB, which is a sorted list. Partition P1 will receive AB again from dataset 2 in a sorted fashion. So partition P1, all it has to do is merge two sorted lists that it received. So A is whatever aggregate value it received from these two data sets, and B, whatever aggregate value it received. So because the data is sorted in the repartition phase, all you got to do is just take in those sorted lists and perform a merge, a linear time operation. So this entire sorting and merging can be done on the disk if you don't have space in memory and the data set is too big. So let's say an analysis of sort merge join. Number one is it can always work because it's a general purpose strategy. The sorting that you're doing, the merging that you're doing, it can be done on disk. But the major downside to it is it's extremely slow because you need to sort data. So it's a n log n operation. And then you have to move all that data, that sorted data, and you have to repartition that. So you're sending this big data over the network. Let's assume the size of this second node was really big. It had huge storage. Then in that case, all you got to do is just move the sorted list from node 1 to node 2. So node 2 will have its sorted list, and node 2 will take the sorted list from node 1, and you can perform the remaining computation on node 2. So your merge can be done on node 2. But this is only if you're lucky that node 1's dataset is pretty small and node 2 storage is pretty big. So in that case, node 2 can do the merge in place rather than sending both node 1's data and node 2's data across the network. Over here, you just have to move node 1's data. But this won't always be the case. For most purposes or for most use cases, you will have to repartition and move both the datasets over the network. But what if one of the datasets could fit in memory? So if one of the datasets could fit in memory, let's optimize and go for the broadcast hash join. Broadcast hash join is extremely simple. You have one of the nodes over here with its big data. You don't do any sorting here. And you have another node with its data as well, but the amount of data is really trivial. It can be fit into memory. So when one of the datasets is massive and the other is pretty small, all you got to do is just move the smaller data set which can fit in memory and broadcast it to the data nodes. So let's say this node over here has the key A, this node over here has key A, this node also has key A, and you want to perform a join. So what you're doing is you're broadcasting this to all the nodes. These nodes will store this data set in memory and they'll do a join in place. So you're assuming a small data set that can fit in memory and a bigger one, which is split across shards. So you have big data that is split across here and here, and you have the common keys that are distributed as well. And you want to perform a join here, here, and here. So you send the small data set to every partition that our big data set resides on. So you're sending this small data to all the other nodes that contain chunks of your big data. So with broadcast hash join, we don't have to sort anything. Just simply iterate over the small data set that you're getting. It is a linear scan, but the amount of data is pretty small, so it doesn't matter. All you got to do is simply iterate over it and then update yourself, create an aggregate of yourself. So just simply iterate over every row of the big data set, check what key matches the key in the hash map, and update your data. So you're doing a linear scan that will be linear over sort, which is n log n. So this is clearly better when one of the dataset size is pretty small. What is the downside? Obviously, there's a lot of network communication over here. You are needlessly sending the smaller data to all partitions. What if this partition, what if the third partition had no key start with A? It had keys like X. In this case, you're unnecessarily sending your smaller data set, broadcasting it to unnecessary nodes. But what if the datasets are too big to fit in memory? So are you forced to go with the first approach, which is a sort merge join? Well, no, we are not forced to. That is always a fallback. It'll always work. It's a general purpose approach. But what we can do is we can go with the third approach, which is partition hash joins. So in partition hash joins, let your initial state be this. Dataset A has 1 million records. Dataset B has 1 million records. And they are possibly unsorted. They are unpartitioned. Step 1, create a partition by join key. So you'll create 100 logical partitions. And all records with the same user ID will obviously land in the same partition. So let's say you have decided to create 100 partitions, so on and so forth, which will in total contain your 1 million plus 1 million records. So let's say partition 1 will have users from IDs 1 to 100. This one will be 101 to 200, etc. Step 2 is distribute these logical partitions across nodes. So node 1 can handle partitions P1, P2, P10. Node 2 can handle the other partitions etc. Step 3. Each partition is small enough to fit in memory. So your joins become very efficient. So again, just to summarize, you had your million records, million students. What you're doing is you're creating logical partitions out of these students. So let's say P1, P2, P3, so on and so forth. And you're assigning ranges to these partitions. That's how partitions work. So let's say this is responsible for students 1 to 100, 101 to 200, so on and so forth. Now, all those students whose IDs are between 1 and 100 that are across these different data sets, they'll all be co-located on the same partition, P1. Similarly, all those students with IDs between 101 and 200 that are scattered across these data sets, when you perform the hash, they'll be relocated to the same partition, P2. Now, the partitions have been chosen in such a way that the partition size is small enough to fit in memory. So P1 can completely fit in memory. Now partition 1 does not necessarily mean that you have a node N1 running only partition 1, having only partition 1. No, partitions are logical concepts. Node N1 can have partition P1, partition P2, all the way to partition P10 as well. The other partitions can reside on the disk. When you want to work with P1, bring it into memory. It can fit in memory, and you can easily do joins. You can perform your aggregate computations over there. So what are the downsides to this? Number one is you're assuming that whatever partitions you've created, the partitions will have equal distribution of data, but that won't always be the case. Number one is your hash functions should be really, really good, but for the most part, they won't guarantee equal distribution. And number two, what if you're partitioning on the basis of names? In that case, you're definitely not going to have equal partition. You're bound to have hot shards. So you can't fit that partition onto the memory. It could be that the partition created is too big to fit in memory, and we need to redistribute all data across the network. So every single data item across these data sets are being moved about the network. So that is a major downside. So in conclusion, ideally during joins, we want both data sets to be partitioned and sorted by the join key, because then we can just send the partitions to the reducer and it just has to merge these two sorted lists. But if this isn't the case, we can either use broadcast hash join or partitioned hash join, or ultimately we have to fall back on sort merge join. Let's now talk about Apache Spark. First, let's see the limitations of MapReduce that makes Spark better for most use cases. Number one is chain jobs in the case of MapReduce don't know about one another. Each new chain job that you trigger is like a totally separate independent task. So let's say you are done with MapReduce task 1 over here. The output of each MapReduce task, if you remember, will be flushed onto HDFS. So when you start the next MapReduce task, as input, you'll load back the data from HDFS and you'll process it and flush it back in again. So a major downside to that is there's tons of disk usage. The jobs materialize intermediate state. So you're forced to materialize or push to the disk all the intermediate states of MapReduce task 1, 2, 3, 4, so on and so forth. But we don't care about all this, right? Ideally, what we like is to load it from HDFS only on input, and only on the final task flush it back to HDFS. Flushing to HDFS is a costly process. You're not only interacting with the underlying HDFS layer, but you also have to deal with replication and interaction with the HDFS name node as well. All this is costly. Every MapReduce job goes from disk to disk, but we only care about the first and last outcome. We don't care about the intermediate state. So it would be great if we come up with a model that avoids flushing to the disk for intermediate states. And I've put a star over here because you will see that in Spark avoids flushing for intermediate states, but for most cases. Some cases you will flush. We'll see that later. On a related note, a second drawback of Apache Spark is you can't proceed with MapReduce task 2 unless all the nodes of MapReduce task 1 are completed. So let's say this is the end of MapReduce task 1 right here. Then you can't proceed with MapReduce task 2 unless all these pipelines are done with MapReduce task 1, because MapReduce task 2 is a totally separate independent job. So you're starting from scratch basically. So in order to start from scratch, your previous state should be set onto the HDFS storage node. Only then can you trigger MapReduce task 2. So that's a major downside. Your pipelines are not actually independent. So in comes Spark. Let's take a look at Spark's architecture. Now, rather than being confined to a strict map, shuffle, reduce phase, in Spark, you can add whatever operation you want. You can add a map operation over here at start. Next, you can add a shuffle operation. In the third phase, you can add another map, another reduce, or another custom operation, custom function that you implement. So Spark is not constrained to a strict map, shuffle, reduce cycle. It can be function 1, custom functionality 2, custom functionality 3 cycle as well. So assume we have 3 nodes in our Hadoop cluster performing some batch computation. It avoids flushing to the disk for the intermediate states for the most part. So in addition, rather than strictly being tied to a MapReduce cycle, we can have any arbitrary function, just provide your custom function, your custom code. And this is huge for modern day real life complex processing. Now remember, with the help of a traditional MapReduce job, map, shuffle, reduce, you can perform any task. But if you have complex functionalities, you will often need to chain multiple MapReduce jobs together in order to achieve your desired outcome. You don't need to do that over here because you're not constrained to these 3 phases. You can add in whatever custom functionality that you want. So relying on just MapReduce forces us to chain multiple MapReduce jobs, which is tedious. Let's take a short detour and understand what narrow dependency and wide dependency is before we go further into Spark. So if this is your pipeline and the input for one stage, for stage 2, is only dependent on the output from the previous stage, which is confined to this pipeline, this is a narrow dependency. So here N2's input is solely coming from the previous stage, which is over here. In the case of a wide dependency, the input for a certain stage is coming from multiple pipelines, is coming from multiple different chains. So the input for stage 2 is coming from this pipeline here and coming from this pipeline here. So in order to start stage 3, you need to have the output from stage 2, that is obvious, and the output from stage 2 of node N2 as well. Only then you can progress. So in a wide dependency, the nodes in this particular layer, in the shuffle layer, when your input data is coming from multiple different pipelines, you can't start with the next stage's computation task unless all the dependencies from the previous stages are resolved. So this kind of dependency is called a wide dependency. Now you can either use Spark with Hadoop. In that case, you'll be making use of Yarn for resource and task management, or you can use Spark outside Hadoop as well. That is standalone Spark. So if you were to use standalone Spark, then the RM equivalent would be something called a Spark Cluster Manager, and the AM equivalent, which is responsible for actually executing your tasks, is called the Spark driver. So using standalone Spark is very ideal in modern day usage rather than using Spark with Hadoop. We prefer to use standalone Spark because in that case, our storage layer is on the cloud. We can use S3 stores rather than being confined to physical HDFS nodes in your Hadoop cluster that you actively have to manage. Using the cloud storage will provide major benefits like auto scaling, and the compute functionality is separate from your storage, and you can only pay for how much compute you're using. You can pay for how much storage you're using. So using it with S3 stores is very ideal. Now for the narrow dependency stage of the pipeline, the output of one stage is used by the next stage, which most likely will reside on the same node. So if N1 is done, the next stage's computation will be done on N1 most likely, because you'll always favor data locality. So in this case, what is the point of flushing the data to HDFS? There's no point in that. You can just store or read from your RAM or your plain hard disk. There's no need to interact with the HDFS layer. So when does it make sense to push stuff to HDFS? Obviously, you'll push it on the final output, final stage, but when would you actually push it in the intermediate states? So checkpointing for intermediate states becomes absolutely crucial when we deal with wide dependencies. So you can see in this stage over here, the processing depends on the outputs coming in from various different pipelines. Now let's say node N1 receives data from this N1 and this N2, and then node 1 shuts down. And then let's say your manager will find out some replica of node N1 and will trigger the Spark job on that. So your N1, let's say, starts from scratch, no big deal. But then when N1 comes at this stage, it also needs data from N2. But N2 is a parallel independent pipeline. N2 might have progressed to this stage. So what will you do in this case? Will you pause N2 and will you restart it and make it run from the scratch, start over here, so that you can get the output to send to N1? That is in this case? No, that'll be really, really expensive, very costly. So it makes sense for N1, once it has resolved all the dependencies it needs in this wide dependency situation, to immediately flush it to HDFS, such that in the occurrence that if N1 were to go down, then the replica, rather than starting from scratch or rather than forcing some other pipeline to start from scratch, it can pick up from the state where the primary node had left off. So it can pick up the data, all the dependencies, and resume from this stage itself. So it makes sense to checkpoint when you have wide dependencies in the intermediate stages. So in Spark, you will checkpoint in the intermediate stages when you have wide dependencies, and you'll also checkpoint in obviously the final stage. So it makes sense to checkpoint to HDFS at this stage to avoid costly shuffling operations and restarting of operations across pipelines were we to restart in the case of wide dependencies. By the way, how do we know about all the narrow and wide dependencies? It is with the help of this dependency graph, and it's created by the application master or the Spark driver on receiving the Spark job from the region node. So it will analyze the Spark job and it will create an appropriate query pipeline, which consists of the graphs, and it will instruct the nodes when to checkpoint and when not to checkpoint. So Spark is aware of the entire pipeline computation graph for a query, allowing it to start computations as soon as all the required dependencies are available from the previous step. So this will all be handled with the help of the application master. The application master will know when all the dependencies for a particular stage, for a particular node is resolved, and can trigger, it can push it to commence with the next stage of computation. So this significantly speeds up the process, and you couldn't do this with the help of plain old MapReduce. So in conclusion, Spark is faster and better than MapReduce. Nodes will do computation as soon as all the dependencies are resolved. All its data that it requires from it and the other pipelines are available. Also, all of the immediate state that we don't need to be writing to HDFS is kept in memory or spilled to local disk. You don't need to unnecessarily flush them to HDFS. The exception is obviously right after we finish a wide dependency, we materialize them to HDFS for fault tolerance. In the next video, we'll talk about stream processing. We'll talk about RabbitMQ and Kafka, and also about Apache Flink.